Here, example 2, that is called to simulate and study the transient response of a series RL circuit. Transient response of a series RL circuit using PSpice, where R is equal to 100 ohms and L is equal to 10 millihenry for the following conditions. These are the two conditions. For these two conditions, we have to execute the experiment by taking the R is equal to 100 ohms and L is equal to 10 millihenry for a series RL circuit. Transient response of a series RL circuit. So here first condition is called source voltage is 10 volts DC with all initial conditions set equal to 0. This is the first condition, and second condition is called source voltage is called 10 volts, same source voltage now no changes. Okay, but with initial conditions IL of 0 minus is equal to 20 milliamps. Okay, these are the initial conditions across the inductor. Initial conditions, current across the inductor is called IL of 0 minus is equal to 20 milliamps. Okay, so for first we have to concentrating on case 1, condition 1. So V of t is equal to 10 into U of t. This expression DC 10 volts can be expressed like this. V of t is equal to 10 into U of t. U of t is called step function. So U of 0 is equal to 1. U of 1 is equal to 1. U of 2 is equal to 1. Irrespective of the time, the U of t is equal to always 1. That 10 into 1 is called always DC. So V of t is equal to 10 into U of t is called our DC voltage in the form of time. So apply Laplace transform on this V of t. So then V of s is equal to 10 by s. V of t, Laplace transform V of t is nothing but 1 by s. So then V of s is equal to 10 by s. And then next current expression, in series RL circuit, IFS is equal to V of s by Z of s. Z is nothing but resistor and inductor. So in terms of S domain is nothing but R plus Ls. Inductor represented by Ls and capacitor 1 by Cs. So I of S is equal to V of S. This is called 10 by S is called V of S by Z of S. Z of S is equal to R plus Ls. By taking the common L and 1 by L, it will become 1 by N and S plus R by L. By taking the common denominator, you will get this expression 1 by L into S plus R by L. So by taking the common 1 by L here, then it equation like this 10 by S into S plus R by L. So this expression by using partial fractions, so separate this, okay, 10 by R into 1 by S minus 1 by S plus RL. By taking the inverse Laplace transform on both sides for this equation, so we will get I of t is equal to 10 by R. So 1 by S, inverse Laplace transform of 1 by S is nothing but 1, and the inverse Laplace transform of 1 by S plus R by L is called e power minus R by L into t. So in this question, by taking the resistance R is equal to 100 ohms, L is equal to 10 millihenry. So by substituting these values in this expression, and this expression will become I of t is equal to 10 by 100 into 1 minus e power minus 10 to the power of 4 t 10 to the power of 4. Time constant is nothing but L by R. By substituting here, then we will get we will get this expression like this. So by substituting the time t is equal to 0 in this expression, I of 0 is nothing but e power 0 is equal to 1. 1 minus 1, 0. That's why I of t is equal to 0. That is called I of 0 is equal to 0 in case condition 1. Similarly, by substituting t is equal to infinity here, so e power infinity is equal to 0. That's why 10 by 100 is called 0.1. That is nothing but 100 milliamps. Okay, and the time constant tau is equal to L by R, and L is nothing but 10 millihenry. R is called 100. By substituting this, will get 100 microseconds. Okay, so in series RL circuit, current is exponentially is increasing. That's why time constant for increasing waveform, time constant is nothing but 0.632. Otherwise, 63% of final steady state value. Our final steady state value is called nothing but t is equal to infinity. That is called 100 milliamps. That means 63% of 100 milliamps. That is equal to 63 milliamps for time constant. For 100 microseconds, this is the this is the current. Okay. So then voltage drop across the resistor is nothing but VR of t is equal to R into I of t. Voltage drop across the resistor VR of t. V is equal to I into R. The R and L are series. That's why VR of t is equal to R into I of t, then R is called 100, R is, what is 100 ohms? R is equal to 100 ohms into I of t is nothing but, this is called I of t is equal to 10 by 100 into 1 minus e power 10 to the power of 4 into t. So like this is the expression. So then 100 cancel, and then it will become 110 into 1 minus e power minus 10 to the power of t 4 into t. Like this, we will get voltage VR of t expression. It's clear? At t is equal to 0, VR of t is equal to 0. By substituting the t is equal to 0 here, 10 minus 1 minus 1. And then t is equal to infinity, VR of t is equal to 10 volts. Okay, this is the expression for voltage drop across the resistor. It's clear. And then voltage drop across the inductor L is VL of t is equal to V of t minus VR of t. So voltage drop across this total voltage minus voltage drop across the resistor is nothing but voltage drop across the inductor. Voltage across the inductor, that is equal to V of t minus VR of t. V of t is the expression V of t 10 into U of t minus VR of t is called 10 minus 10 into e power minus 10 to the power of 4. So that's why you will get only 10 into e power minus 10 to the power of 4 into t. Only this expression. Okay, by substituting the t is equal to 0 in this expression, so VL of t is equal to 10 volts. E power 0, 1. That's why VL of t is equal to 10 volts. Similarly, t is equal to infinity. So by substituting this t is equal to infinity in this expression, then VL of t is equal to 0. So voltage across the inductor under steady state condition is equal to 0 because of under steady state condition inductor acts as a short circuit. So that's why during short circuit condition voltage 0. So by plotting these curves like this, we will get this type of curves. So I of t is called current flowing through the inductor is exponentially increasing. During transient condition, it is not allowed the sudden changes in current. That's why transient condition is the current in the inductor is equal to 0. So then after that, it is exponentially is increasing. And then finally, inductor short circuit. That's why maximum current flows to the circuit through the inductor. So like this, so we will get this waveform. And for exponentially increasing waveform, time constant is nothing but L by R for RL circuit. So for 100 milliamps, so 0.632 times 63.2 amps, 0.632 times of 100 milliamps is nothing but 63 milliamps. So this is called IFT expression. And then, so we have to execute this experiment and piecewise, then we will get same results. So similarly, we have to find the voltage drop across the resistor. VR of t is equal to like this. Voltage across the resistor. Voltage across the resistor during transient condition, inductor not allow the sudden changes in current. That's why current is also 0. So voltage drop across the resistor is also VR of t is equal to R into I of t. Current 0, transient condition. That's why voltage drop also 0. And then final condition, inductor acts as a short circuit. That's why current is maximum. So maximum during t is equal to infinity, the current is maximum. That's why voltage drop also maximum across the resistor. And then next to voltage across the inductor. Voltage across the inductor is nothing but transient condition. Inductor not allow the sudden changes in voltage, sudden changes in current. That's why it acts as open circuit. During open circuit condition, supply voltage present across the inductor. And finally, inductor acts as a short circuit. During steady state condition, inductor acts as a short circuit. So during short circuit condition, the voltage is equal to 0. That's why the exponential is decreasing in this way. So this experiment we have to execute by using PSpice. Okay, go to PSpice and RL circuit. So take one source that is called VDC. VDC, place here and take one resistor, otherwise T close switch, place here closer switch, and then take one resistor RL circuit. Take one resistor R. Similarly, take one inductor L and press controller. Okay, controller and place and here and take one ground also. Ground. Take one ground. Connect here. Okay. Take one wire. Connect. circuit like this, and then like this way. Okay, connect like this, and zoom to fit. So this is the series RL circuit. Series RL circuit. Here, what is the our input voltage for a series RL circuit? What is the condition here? Source voltage is called 10 volts DC. Source voltage is called 10 volts DC. Here 10 voltage. 10 volts is DC, and the resistance is called, what is the resistance? 100 ohms. Inductance 10 millihenry. Resistance is equal to 100 ohms. Value of resistance is called 100 ohms. And save all the, okay. And inductance is how much here? Inductance is equal to 10 millihenry. 10 millihenry. 10 mH. And also initial conditions are 0. No? Initial conditions 0. That's why here 0. Enter 0. Save alter and then okay. And connect it like this. Okay. So like this circuit is designed. Then after that, what is the time constant here? Time constant is nothing but 100 microseconds. So final steady state time is called 5 time constant. That is called 500 microseconds. Okay. Final steady state time is nothing but 500 microseconds. So that's why greater than we have to give final steady state is nothing but final value is nothing but greater than this time 5 time constant 500 microseconds. So that's why here go to analysis, setup, and enable transits, this box. Okay, enable this box, small box, and go to transient, and here what is the time? 5 time constant is nothing but 500 microseconds. No? So that's why, so 700 microseconds. Let us assume this here time is nothing but 700 microseconds. Then what type of graph we will observe? Okay, so after this press simulate, and then before going to simulate, save. This is called transient TRE, transient for RL circuit, transient for RL, transient RL. Then simulate, and then before going to simulate, take one voltage marker or current marker. So first we have to analyze what is this, what is the expression? I of t expression. That's why, so I have to take current marker I of t, place here. Okay, current marker place here, on inductor terminal, not place on wire, and terminal of inductor place like this, and then simulate again. Press simulate and then open like this. So this is the our output expression. Change pulse width like this, and this is our waveform exponentially increasing. Exponentially is increasing. So up to 100 milliamps, na? Up to 100 milliamps. Exponentially increasing up to 100 milliamps. This is called 100 milliamps. Okay, like this waveform is increases like this. So 5 time constant is nothing but 500 microseconds. Okay, so in this 5 here, what is the time constant is called? 100 microseconds. 5 time constant is nothing but 500 microseconds. Okay, and this is called final steady state value, and time constant at 100 microseconds is nothing but for 100 microseconds. So this is the voltage, this is the current, 63 milliamps. 63 milliamps. Time constant is here 100 microseconds. 100 microseconds. So to enable toggle cursor and place here, and how much voltage, how much current here for 100 microseconds, 63.108 milliamps. So mark label like this. This is about how the voltage across the current across the inductor increases, exponentially increases, and then how to find the time constant. Okay, this is way we have to observe this exponential increasing. And next waveform is called voltage across the resistor. VR of t is also exponentially is increasing. So in this schematic, voltage across the resistor, no? So voltage, that's why take voltage marker. voltage across the resistor. That's why take voltage marker, remove current marker, take voltage marker. That means go to markers here, mark voltage differential, place positive here and place negative here. This is called difference between difference across voltage across the resistor. Okay, like this place. Go to markers, mark voltage difference, then place here positive, here negative. Okay, this is called voltage across the resistor, and then run, simulate, and then like this exponential is increasing up to 10 volts. The voltage across the inductor is called voltage across the resistor is 10 volts now. Here 10 volts, and the same way here also this is the voltage across the resistor is called 10 volts. So final steady state voltage is nothing but 10 volts. For 500 microseconds is called steady state time. T is equal to infinity. This is called final steady state time. This is called final steady state. So 500 microseconds, 9.99 approximately 10. So this way the voltage drop across the resistor we have to understand by using PSpice. And the next VL of T, voltage across the inductor. Okay, voltage across the inductor exponentially decreasing from 10 voltage 10 onwards. So that's why remove this voltage marker across the resistor and connect one voltage VL voltage marker across the inductor. And then how voltage changes across the inductor. So voltage across the inductor we are expecting this exponentially decreasing manner. So that's why, so simulate, connected, and then simulate exponentially decreasing waveform. Okay, so like this exponentially is decreasing waveform. Then 500 up to 500 microseconds. It will take time up to 500 microseconds. Okay, this is for case 1. Okay, case 1, this way this experiment is executed. And the next, coming to the next case 2, that is called V of t is equal to 10 into U of t. Here initial conditions we have to take, we have to concentrating on initial conditions. Condition 2 is called, by taking initial conditions we have to execute this experiment. So V of t is equal to 10 into U of t, no changes in source, source voltage as it is same as case 1, but case 2 only initial conditions, L of 0 minus is equal to 20 milliamps. Then apply Laplace transform here, the V of s is equal to 10 by s. Then next V of s expression from series RL circuit, V of t is equal to I into R of t plus L into d of d by dt. So V of t is equal to R of t plus L into di of t by dt. This is expression. Okay. So VR of t is equal to nothing but I of t into R. VR of t is equal to here. VR of t is nothing but voltage across the resistor is nothing but R into I of s. By applying Laplace transform, then V of s is equal to R into I of s plus L into S into I of s. Initial conditions are existed. That's why we have to take like this. Initial, this is called minus I of 0. S into I of s minus I of 0. So substitute initial conditions here. 20 into 10 to the power minus 3. Then simplify this expression. And then you will get like this. I of s is equal to 0.022 by s plus 10 to the power 4 plus z10 cube by s into s plus 10 to the power 4. So apply inverse Laplace transform, inverse Laplace transform on this equation. Then you will get I of t is equal to 0.1 minus 0.08 into 10 to the power into 10 to the power 4 into t. So in this expression, by substituting the values of t is equal to 0, e power 0, 0.1 minus 0.08, that is equal to 0.2, otherwise 20 milliamps. Okay, by substituting the value of t is equal to 0 in this expression, we will get like this. T is equal to 20 milliamps. Then at t is equal to infinity, substitute here, at t is equal to infinity, this expression will become 0 and it will be only 0.1, that is called 100 milliamps. Okay. And then next voltage drop across the resistor R. VR of t is nothing but R into I of t. So this is the expression for I of t. Then R into I of t is nothing but R 100 into I of t. Then 100 into 0.1 minus 0.08 into 10 to the power minus 10 to the power 4 into t. Simplify and then we will get like this. 10 minus 8 into 10 to the power of minus 10 to the power of 4 into t. So substitute here also t is equal to 0. Then VR of t is equal to 2 volts. Substitute here. T is equal to 0 means e power 0, 1, e power 0, 1, and 10 minus 8 is nothing but 2. 10 minus 8 is equal to 2. So at t is equal to 0, VR of t is equal to 2 volts. Okay, at t is equal to infinity, VR of t is equal to 10 volts. So if t is equal to infinity means e power minus infinity is called 0. That's why only 10. VR of t is equal to 10 volts. Similarly, voltage drop across inductor. Voltage drop across the inductor is called VL of t is equal to V of t minus VR of t. Then here 10, 10 cancel and then it will become minus become plus because of minus VR of t. No? That's why 8 into e power minus 10 to the power of 4 into t. So at t is equal to 0, substitute here. At t is equal to 0, e power 0, 1 and the V of t is equal to 8 volts. Voltage across the inductor is called 8 volts. At t is equal to infinity, VL of t is equal to 0. So this is the expressions voltage across the first voltage current expression, then after voltage across the resistor, and then voltage across the inductor. So for this is we have to execute by using PSpice. So only initial conditions we have to change here. Same, everything is same. R is equal to 100 and 10 millihenry. Source voltage is called 10 volts. So here initial conditions 0 na previous case. Now I'm changing to initial conditions called 20 milliamps. 20 milliamps. Save alter and then okay. Okay. So first we have to concentrating on what is the expression I of t, current I of t. So I of t expression. So remove this voltage marker and place current I of t. So I of t place in this. IL of t or IR of t both are same because of series. For series connection, current is same. And then simulate. So like this we will get. Okay. So initial conditions is called 20 milliamps. 20 milliamps. It's like 20 milliamps. 20 milliamps like this. Save order, then okay. Then simulate. And we are getting an expression. So in this way. IL of t is equal to 0 amps, milliamps. That's this width. So in this analysis, open inductor initial conditions here IC is equal to, so give minus 20 milliamps initial conditions, and then save alt okay, then okay, then we will get perfect waveform. So simulate and then so here so, change the pulse width of this waveform, then you can easily understand. This is called minus 20 milliamps. Enable toggle cursor here 20 milliamps. Okay, from 20 milliamps onwards, this waveform will start. Okay, so exponential is increasing, and then final current is called T is equal to infinity, 100 milliamps. And under steady state condition, this is called 100 milliamps. Let's settle to 100 milliamps like this. So we have to execute this experiment. And this is called voltage current in series in current diopter expression. Okay, so for example, if it is current IFT is connected across the resistor, both are series na same expression we will get. So like this, if you are connecting current marker at resistor, same expression we are getting because of series or both the resistor and inductor are connected in series na. So that is called with initial conditions and current IFT expression. Then voltage drop across the resistor. Voltage drop across resistor is next voltage drop across the resistor is called this is this no voltage drop across the resistor. Go to markers, mark voltage differential. This is called plus and this is called minus. The one voltage across the resistor. Okay. So here inductor initial conditions 20 milliamps. Then simulate and then change comes with. So this is the voltage here. 2 volts was 0, 1, 2, 3, 4, 5. Na? So from 2 onwards, this expression will start like this. Voltage drop across the inductor, voltage drop across the resistor, it changes like this. Here 2 volts, and then exponential is increasing from 0 onwards. Okay, and your final steady state voltage is called 10 volts. This is the voltage drop across the resistor. Similarly, voltage drop across the inductor. Okay, voltage drop across the inductor. T is equal to 0, so we will have T is equal to 8 volts. At T is equal to infinity, we will have exponentially decreasing from 8 volts onwards. Okay, delete. So what is this voltage across the inductor? So take one voltage marker, place here one voltage marker and simulate, and then open like this. The voltage across the inductor is decreases this way. For condition 2, so these are the different circuits for RL circuit. For case 1, initial condition 0. Here initial conditions come 10 milliamps. For second case, and step is equal to 0 seconds, and the final time is equal to 500 milliseconds. Okay. Then you will get simulate an individual circuit and another plot like this. This is the question. So we are done.